Next, we're going to talk about two conventions for counting. So we're going to count how many possibilities there are. Remember, we talked about probability being essentially coming down to how many ways we could win versus how many ways total there are in this set. So sometimes we need to count in very elaborate fashion how many different ways we could win or how many different ways something could happen, all right, versus how many different ways could happen that are really bad for our company, or how many different ways where we win money. So there are two ways which we'll go over next part of class. One is called permutations, where the order in which things happen matter, and the other is combinations, in which the order does not matter. We just want to know how many different possible combinations there are. So we will start with permutations, in which order matters. If you don't know what I mean by order matters, I will explain that right now. Suppose we have 1, 2, 3, 4, 5 people: Jack, Sally, Fred, Martha, and Bev. Suppose they are all going to run a race. How many different ways could these 5 people place first, second, third, fourth, and fifth? Not quite. There's 5 different people who could win, but for each of those 5 people who could win, there's 4 different people who could get second place. And then there's so on and so forth. So Jack could win. So it could be like this. It could be Jack, Sally, Fred, Martha, Bev. That's one way. First place, second place, third place, fourth place, fifth place. Or Jack could get first place, Bev could get second place, Sally could be third, fourth, fifth. Or Jack could get first place, Martha could get second place, Sally da-da-da-da. So more than 5. There are more than 5 ways in which they could place first, second, or third. But I like to look at it this way. There are 5 different people who could... I just don't have to repeat this once Dr. Williams comes back. There are 5 different people who could win. Now, if Jack wins, suppose he's one of 5 people who could win. How many people could get second place?
4.
Yes, if Jack wins, there are 4 different people who could get second place. Right? And Jack's not the only person who could win. All 5 of these people could win. So 5 different people could win, and of those 5 people, there's 4 remaining people who could get second place. So there's 20 possibilities right there. You with me, Shiva? 5 different first place winners. And for each of those 5 different winners, there are 4 different ways that second place could happen.
Okay.
So for each of those, not only that, we can go on. There are a remainder of 3 people. So for each of those first and second place winners, there are 3 different third place winners. And then there are 2 different fourth place winners, and that would leave 1 different fifth place winner. So, in answer to the question, how many different ways could these 5 people place first, second, third, fourth, and fifth? We take the total number, 5, times the number of possible second place finishers, given that any of those 5 people win, times the number of third place finishers, times the number of fourth place finishers, times the number of fifth place finishers. 5 times 4 is 20, times 3 is 60, times 2 is 120. All right, that's it. There are 120 different ways that these 5 people could come in first, second, third, fourth, and fifth. I will show you a shortcut very shortly. But first, I just want you to understand that's how we did the math. Let me ask you another question. How many different ways could these 5 people place first, second, and third? That is correct. 5 times 4 times 3. So there are 5 different people who could get first place. For any one of them, there are 4 combinations of second place. So if Jack wins, 4 different people could get second place. Sally wins, 4 different people who could get second place. Fred wins, 4 other people who get second place. Martha wins, 4 other people. Bev gets first place, 4 other people. So we've got 20 combinations right there. And we could keep going on and on. Third place, fourth place, fifth place. If we only care about the first 3 places, 5 times 4 times 3, 5 times 4 is 20 times 3 is 60. So there are 60 different ways that first, second, and third place could be assigned. Before I show you the formula, I need to show you one little mathematical symbol. It is the factorial sign. So 5 factorial. Has anyone seen that before? Nikita, you've seen it before? What it means, when you see that sign, 5 factorial, that means you take 5 times 4 times 3 times 2 times 1, all the way down to 1. So that means this equals 5 times 4 times 3 times 2 times 1 equals 120. All right, what if I were to give you this? 3 factorial.
3 times 2 times 4.
Yes. 3 times 2 times 1 equals what? 6. Does that make sense, Shiva?
Yeah.
Fantastic. Well, let me give you a really easy one. 2 factorial. 2 times 1 equals 6, right? 2. Just joking. One little thing you need to be aware of, when you get down to 0 factorial, the answer to that is 1. It's not 0, it's 1. If you should ever come across 0 factorial, it's 1. You just need to remember it. I'm not sure exactly how mathematicians define it or explain it. 0 factorial equals 1. So, that brings us to our shortcut for permutations when order matters. It is this equation. N things taken r at a time is n factorial divided by n minus r factorial. So, suppose we have 5 things. We have 5 people. And suppose we want the permutation, because order matters. We have 5 people, and we want to know how many different ways they can place first, second, third, fourth, and fifth. So we're concerned about all 5 places equals in this n factorial. So it's 5 factorial divided by n minus r. 5 minus 5 factorial. Okay, and we know that 5 factorial equals what? 120. Because we've already calculated that. That just means 5 times 4 times 3 times 2 times 1 was 120. We did it again. 5 times 4, 120. So now we've got 120 on the top. All right, and on the bottom, we've got 5 minus 5, which equals 0 factorial. What does 0 factorial equal? 1. Okay. So the answer is 120. So that works out. That's the same way we guessed. We reasoned that there are 5 different people. How many different ways could they place first, second, third, fourth, and fifth? 120 is the answer.
So we don't have to do any calculation for like 5 each 5 and b. Yeah.
What?
We don't have to calculate this one.
Well, we did 5 factorial, is 120, and then 5 minus 5 is 0. So we took 0 factorial, and we know that's 1. So we get 120 over 1 equals 120. There's another question? Maybe you're just getting hung up on some weird way it's notated. We'll try another example, and you still have a question, of course, to ask. So let's try the second thing we did. How many different ways could they place first, second, and third? So in this situation, permutation, all right, because order matters, we have 5 total things, but we only care about the first 3. So 5 things, taken 3 at a time. We put it into this formula. Alright, we're going to get 5 factorial divided by 5 minus 3 factorial. That's going to equal, remember 5 factorial is equals what, Shiva? 5 times 4 times 3 times 2 times 1?
Right. So it's 120.
Yes. 120 over 5 minus 3, we'll just write it 2 factorial. Right, and what does 2 factorial equal? Which is?
2.
Yes. 120 over 2 equals 60. That's what we came up with, right? Bingo. Is that all making sense? So we've got permutations, order matters. We've got a formula. We know one little thing we need to know. 0 factorial equals 1. Makes everything add up nice and right.
So is that 5, 4, 3, 2, 1? That indicates order matters, right? I mean, is that what you're saying?
Permutations order matters. We went through an example of how we might reason through the total number of possible places, possible ways these 5 people could finish first, second, third, fourth, and 5th. This doesn't necessarily mean order matters the way I've written that, though. Okay, any other questions? All right, let me erase this and we'll talk about combinations. All right. Order does not matter. Okay, so in this case, we just want combinations. We don't care what order they're in. Ann, Ward, Jen, and Al. I guess I like using different names. Let's see here. Ann, Ward, Jen, and Al. All right. How many different combinations of teams of 2 could we have? Okay, so we've got these 1, 2, 3, 4 folks. The question for you is how many different combinations could we have for teams of 2? Different combinations for teams of 2. It's out of our way. So let's think it through. Well, we could have Ann and Ward. That's 1 team, right? Okay. We could also have Ann and Jen. That's 2 teams. We could also have Ann and Al. That's 3 teams. All right. And we could have Ward and Ann. Have we already gotten that one? All right. We've already gotten that. I threw you a curveball. We've already have Ann and Ward as 1. Ann and Jen is 2. Ann and Al is 3. So let's look at teams of just Ward. We've already got Ann and Ward. We've already counted that in our 3. We could also have Ward and Jen. That's 4. Then we could have Ward and Al. That's 5. Now how about teams with just Jen? We've already got Ward and Jen and Ann and Jen. So how about Jen and Al? That's 6 total. And then Al, we've already accounted for all the combinations of him being on the team. So combinations, 6. There are 6 combinations. Now note, we do not care who the first person on the team and the second person on the team is. We just want combinations, order doesn't matter. We know for these 4 people, there are 6 possible combinations. We can write this in terms of a shortcut formula. All right, combinations, order doesn't matter, n things taken r at a time equals n factorial divided by n minus r factorial times r factorial. So let's try the combination we just worked out and hope that it comes out to 6. Okay, so that would equal n, we've got 4 things, so 4 factorial divided by n minus r. We've 4 things taken 4 at a time, so 4 possible, and we want combinations of 2. Sorry about that. So 4 total things, we want combinations of 2. N factorial on the top. On the bottom, we've got n minus r, which is 4 minus 2 factorial, divided by r factorial, which is 2 factorial. Okay, let's simplify that down a little more. So we've got
divided by r times r.
Times r on the bottom, but it's going to be
Yeah.
it's going to be divided by. So 4 factorial on the top, divided by 4 minus 2 is 2 factorial times 2 factorial. Alright? Equals, what's 4 factorial? 4.
24.
4 times 3 is 2 times 2 is 24. Okay? So we've got 24, it's 4 factorial. Then we've got 2 factorial, it's 2 times 1. So 2 times 1 is 2 times 2 equals 24 divided by 4 equals 6. Okay? Rockin' and rollin', right? Any questions on that? Let's try a couple examples, just get that ingrained. Let's turn to page 484, and let's do problem number 2. And that is 3 factorial. Just go ahead and do that on your own. We'll come back together in 30 seconds.
You said 484.
Yeah, 484. Page 484, problem 2 we're starting with. All right, everyone there? All right, so the question is 3 factorial. Let's crank that out. Equals 3 times 2 times 1 equals 6. Bingo. Questions? Let's do number 6. Okay, now this one you could do, I'll tell you it's 7 factorial. So this brings up an important point. You don't want to do these in your head. You don't even want to do them in your calculator. You want to find the button on your calculator that allows you to do it in one stroke.
7 raised to 2.
What?
7 raised to 2.
No. There should be a factorial button on your calculator. Yeah. See this X factorial button right there above my thumb? So let's do, so that means you're going to hit the second. So you're going to get 3 second X factorial, 6. Bingo. All right, try it. Give me 3 factorial. Yeah. So now try 7 factorial. There you go. Sure, you got it. You hit the second, and then just, yep. All right, what do you got? You got a factorial button? So the shift, so hit 3, shift, hit 3, shift, equals.
Oh, okay.
Bingo. You have the factorial on that finance calculator?
Yes, sir.
Excellent. Okay. So, Shiva, what do you get when you calculate 7 factorial? 5,040. I like it. What number are we doing again? Yep, that's right. 5,040 is correct. All right, let's move on. Number 12. Permutations. 9 things taken 5 at a time. Yep. Let's do number 12. Wait a minute.
So, for 6.
Yep.
We don't have to do anything about
Oh yeah. You know, I'm sorry. I looked at the wrong one. I was looking at 4. 4 is 7 factorial. And the correct answer to 7 factorial is what Shiva told us. So now let's do 6. Let's actually do 6. I'm sorry. I need to put my glasses back on. 6 is combination. 7 things, 2 at a time. All right, Nikita. As soon as you have it, just blurt it out. You too, Shiva. You gotta just blurt it out. Close. Close. Take a guess, Shiva. Did you, Nikita, did you forget this little extra? You got it? 7 combination, 2 at a time. Six, 7 combinations. I'll try one more time, Nikita. You still got that answer, we'll work it out. Yes.
42.
21 is the correct answer. All right, let's work it out. So 7 factorial divided by 7 minus 2 factorial is 5 factorial times 2 factorial. All right, so what is, Shiva told us what 7 factorial was. It was 5,040, right?
Yes.
All right, what is 5 factorial? Yeah, 120. We started out class with that. 120, and what is 2 factorial?
So 2.
2 times 2. Okay, 120 times 2 is 240, so that's 5,040 divided by 240 equals 21. I like it. Makes sense, Shiva?
Yes.
Dr. Williams? All right, we're going to be moving on to problem 12. Start 12 at your leisure. If you still have questions about this, I will be happy to answer it. The 12 is going to be permutations. 9 things taken 5 at a time. Permutations. Be sure to use the permutation formula, not the combination formula. Permutations. 9 things taken 5 at a time. Dr. Williams? Shiva?
There's 5 factorial.
What's the answer? Did you get the answer?
Oh, I think I got
20? Okay, all right, let's work it out. So, all right, so we've got 9 factorial on top.
Oh, it's 9.
Okay, all right, so it's definitely going to give you the wrong answer. All right, but we'll get the right answer this time. And then on the bottom, we've got 9 minus 5 factorial. 9 minus 5 factorial times 5 factorial. All right, top we still have 9 factorial. Over 9 minus 5 is 4, right? So 4 factorial times 5 factorial.
5?
What?
I think we are doing permutations, so we don't have to take 5 factorial.
Yeah. Are we doing permutations? Combination?
Points. Good point. Thank you, Nikita. Permutations, order matters. So there's going to be actually more of them. Sorry about that. So 9 factorial divided by 9 minus 5 factorial, and we're done. That's it. That's all we need to do. Equals 9 factorial divided by 4 factorial equals 15,000 something?
15,120.
15,120? Is that right? Okay. Feeling comfortable with mechanics? Even though sometimes you need to get used to the calculator. All right, are we ready to move on? Let's do just a couple more. Let's do number 38. So a baseball team has 15 players. How many 9-player batting orders are possible? So there are 15 total players, and we want to create the batting order. Now, apparently, this is one of those situations where the order matters. So when you're creating the batting order, you want like the small players who can like get a base hit to bat first. You also want the strongest players, the people who are going to start off with the momentum to bat early on in the order. And then maybe as you get into third or fourth batter, you want the heavy hitters, the ones who can maybe knock a home run. So order matters in this. So let's calculate a permutation because order matters. All right, so permutation.
But they're not asking that, though. They say how many 9-player batting orders are possible. They just wonder how many 9 combinations are possible.
Well, batting orders. Yeah, how many 9-player batting orders? So meaning different orders. How many 9-player batting orders are possible? So Sheba could be first. Nikita could be first. They're not saying just give me 9 players. They're saying in what order do we want these? So 15. Taking 9 at a time. We're going to use our permutations formula, right? So we're going to take 15 factorial divided by 15 minus 9 factorial. And we're done. So that's going to be 15 factorial over 6 factorial, right? So we punch 15 factorial in our calculators, divided by 6 factorial. Or maybe you save it in your calculator, and then crunch out 6 factorial, and recall that number you saved. Maybe you write it down on a piece of paper.
But it doesn't, computer, but it doesn't go to 15 factorial. I mean, it gives it 1 point answer.
It gives you in scientific notation.
Yeah, scientific notation. So 15 factorial is 1.3076
Times 10 to the 12.
4 to the 12.
Yeah. So just keep that in your calculator, and then divide by 6 factorial. So enter 6. Where's the factorial?
Blue 3.
Divided by. And 0. What do you get, Nikita?
181621440.
1.8 million, right? And you can, where'd you have in your
No, it's 1.8 billion.
1.816.
Oh, 1.8 billion. Sorry about that. Billion with a B. 1.8 billion. You don't like Shiba, you don't like their other calculator? Okay, fine. Okay. Yeah, oh, you got it. You got the right answer.
Right.
Shh, what am I even worried about? You're way ahead of me. All right, let's do one more. Let's do 49. The college football team has 11 seniors. The team needs to elect a group of 4 senior co-captains. How many different 4-person groups of co-captains are possible? Now, they're asking for co-captains. They're not saying you're number 1 captain, you're number 2 captain. They're all co-captains. So does order matter in this case? Yeah, order does not matter, so we're looking for combinations. 11 seniors, taking 4 at a time. So we want a combination, 11, 4 at a time. Get this junk out of the way. Okay, so what do we need here? We need 11 factorial. Right, red. Makes me feel like I'm more distinguished. All right, 11 factorial divided by 11 minus 4 factorial times 4 factorial. Okay, that's going to equal 11 factorial divided divided by 7 factorial times 4 factorial. All right. I hope you're familiar with your calculator at this point. It's the only thing that's going to save you.
19080.
I get a different answer. What do you get? Man. 11 seniors, 4 at a time. Keep in mind, as soon as you get this one right, we get to go home. Don't mean to put any pressure on you. If you get it wrong, we have to stay. This is like forced math problems.
4.8283366 12 an hour.
What'd you say? 4.2?
828.
4 point? Like a fraction? Like 4.8?
No, it's 4 billion. I mean, it's a big number.
4 billion? Alright, I'm not liking 4 billion. I think that's wrong. Should make this like you get to go home as soon as you get it right. So Nikita got it right, so she gets to go. Everyone else is to stay. That's your pass out of here. I'll start packing up. Is that a minus? Did you do minus? Or divided by?
I think
It's a minus. It's divided by. And you need parentheses too. You need divided by parentheses. Try that. Divided by parentheses. 7 factorial. Put in 7 factorial. Times 4 factorial. Close parentheses. Yes. Equals 330.
330.
330. Bingo. 330 different combinations are possible. Great work tonight, folks. It's 9, although it doesn't feel late. Right? We were energized by this. I feel like everything was clear in terms of the material from last week. It took some time to go over it, but I feel like we got comfortable with that. And then we really didn't add much. We added expected value, permutations, and combinations. Random variables, but expected value was the punchline to random variables.
So, Professor, next week and this week and we have to do 4 quizzes in a row. So, the upcoming part.
Yeah, but you're going to have all the answers to the first 3. So, does that work?
yes.
Yeah.
You want to try to get all 4 of those done by the time you walk in here next week?
Yes.
Fantastic.
Thank you.
You bet. Look forward to seeing you next week.